And all right, so the outlines are shown here. So I'll talk about some motivation in the background. This actually will take a lot of time. And then I'll move on to some technical details. We need to know what are the ribbons, and we need to know exactly what's the quantum double model. And we'll move on to subphases derived from the quantum double phase. By a phase, I mean anyon theory. And then I'll mention, this is the first important thing in my work, that what's the anyon trinomial map. I'll talk about what it is, and then the relation between this map and the Floquet code. And at the end, I'll talk about the generalization of this picture to move on from the quantum double to generic modular tensor categories. All right, so the first motivation of this work is originally try to generalize the Floquet code. It was the first given by Hastings Hen, and then they also show up in Margarita's paper and Catherine's paper. So we'll see that we don't have to constrain ourselves to single phase to do the topological quantum computation. Neither do we need to restrict to periodic phase transitions, isomorphic phase transitions. That's what happens in the original Floquet code. Instead, we can consider quantum computation with non-periodic and non-isomorphic phases inserted in both temporal. This is what happens in Floquet code, and also spatial directions. Well, we know this before. This is called quantum computation with gap boundaries. A gap boundary is actually a trivial phase. Here, my claim is just that we can consider no more than just trivial phase. We can insert something more. And please feel free to interrupt me if you have any questions and I'm not clear on some things. All right, so advantage of this is that in each phase, the logical gates, the universal side of logical gates are different. So if in one phase, some gates are hard to reach, has higher complexity, and then in another phase, it might be easier to access. And not just that, the phase transition itself can also be viewed as a logical gate if we preserve the logical information. So it can also help us enrich our arsenal in quantum computing. All right, so this is, I want to spend some time on the review of the Floquet code. So this is the color code, and the Q dates lie on the vertices of each hexagon. And the Hamiltonian is given by this. Each plaquette has a product of 6 poly X and 6 poly Z for each plaquette. It's just that we color different plaquettes with 3 different colors. Therefore, this theory, we have 9 3x3 different bosons, 3 different colors and 3 different poly labels. And here, this is the fusion rule. So what's the Floquet code? It can be viewed as, what I've shown before is the color code phase. And here, there are the 6 steps of different subphases of the original theory. In the original theory, there are 9 bosons, and there's actually a way to map it to 2 copies of toric code. And 2 copies of the toric code is isomorphic quantum double of Z2 times Z2, the product group. And the Floquet code can be viewed as different condensations. So a black disk means this boson is condensed, and cross means the boson will not appear. It's confined in the subphase after the condensation happens. E and M are the E and M anyons in the toric code, because in toric code we have E and M and F and 1. 1 is vacuum. So because it's isomorphic to 2 copies of toric code, after we condense with 1 copy, we discard this copy, and we're left with 1 copy. So that's why we have E and M. Here, there are 2 disks. It means they will be mapped to the same thing, E. All right, so there are 6 steps in the periodic phase transitions. Each step is actually a isomorphism. From 1 to 1, this is the identity map that preserves the. So one can also consider E is permitted to M is permitted to E. But here, I will show later how to calculate this in general. It's just that here it's kind of trivial. So we have known a lot about condensation-induced phase transitions and what type of anyons are condensed to a specific boundary. And for example, people must have heard that the rough boundary, it's actually an E condensed boundary. It means that the anyon E is condensed to the gap boundary, and smooth boundary means M is condensed to smooth boundary in the Tori code. So these are what I showed before is actually called condensable algebra. For gapped boundary, it's called Lagrangian. It corresponds to Lagrangian algebra, and for gapless boundary, it corresponds to non-Lagrangian. This is a figure adapted from Xiaogang and Arco's paper. And here, this is phase transitions for the quantum double of the S3 group. S3 is the permutation group, where in the middle, the condensable algebra is just trivially 1. It means nothing is condensed. It remains the original model. And for the 4 subphases in corner, the 4 blue ones, they are maximally condensed, or they correspond to Lagrangian algebra. It means the subphase will be trivial. This is a trivial topological order. And the remaining 3 is not trivial. We only partially condense some of the bosons, and we are left with either Tori code, which is gauge Z2, or the Z3 Tori code. So this is one example. So the question is, we not only want to know what is mapped to 1, what is condensed, we also want to know how our anyons are mapped generally. Like, I want to know what is mapped to E in the Tori code, what is mapped to M. All right. So we need an explicit formula for that. So to answer this question, we need to take a quick review on Kataya's quantum double model that was released like 20 years ago. This is a direct generalization of the Tori code where the group G is just Z2. And this is, one can generalize this further to Lemon-Win model, which uses the fusion category instead of groups. So there will be a bunch of technical details. You don't need to remember or like follow immediately what they are, just give you a feeling and just pay attention to the punchlines. So here, I show here, there are a bunch of triangles. So I want to talk about and define what is the ribbon operator on the lattice. Presumably, we are acting on the ground state, maybe. And then to define a generic ribbon operator, we want to start with one single. It's made of a bunch of triangles. We want to focus on first on triangles. So if it's the cuties lie on the edges of the lattice, and here, what I draw here are 2 different types. One is dual triangle, the other is direct triangle. Dual triangle is the one that has the base on the solid line. The solid line is this. That's a direct triangle. Apologies. And here this is a dual triangle where the base is on the dashed lines. And so after we So corresponding to the dual triangle, we define this operator L. L means the multiplication. It's either to left or right. Multiplication where we assign the qubit a group structure. So the qubit dimension will be the order of the group, the finite group. And then corresponding to the direct triangle, we assign another operator with a projection to the specific label state. Okay, so this defines the operator on a single triangle. There are plus sign and minus sign. They depend on the orientation. So yeah, just let's not worry about the details. Just remember this is a multiplication and this is a projection. So after this, we can define longer ribbons by this gluing formula. And the A terms, there are A terms and B terms in the Hamiltonian. A terms is the product of 4 dual triangles. That means there are 4 multiplication here on the 4 qubits. And B is a projection to G label. It means we multiply the 4 group elements on the 4 qubits and then check if it's the same as the label G. And then AS is defined as summation over A, and B is a projection to E, to the unit of the group. So this will be the local Hamiltonian terms. And once again, we don't need to remember the details, just we only need to know.
Will be the A and B in the protocol.
Oh, I'm gonna say that, thanks. So just remember the Rabin operators are explicitly known. So this is actually a commuting projector model. It means everything commute, and each term, local term, is a projector. So that means the theory is exactly soluble. It's a theory that's not as easily understandable. And in the toric code, then that means G is Z2 group, and A terms will be XXX, because what I said is that the A terms will be product, and in the toric code, there's only one attribute product, which is a flip. That's X. All right. So the first theorem I want to mention here, this is in Baumi-Hector's paper. The operator we defined before, they're actually quite useful. They commute with every Hamiltonian local terms in the Hamiltonian, except the local terms at the 2 ends of the ribbon. So they generate all 2-point excitations or pairwise excitations. Okay, let's go back to our main topic. Recall that we are interested in anyon tunneling map. We try to figure out what anyon is mapped to another. Yeah, please.
Sorry, so for these ribbons, they will collapse to like normal strength operators if you have an abelian.
Yes.
I see. Okay, perfect, great.
Yeah, that's true. That's a very good intuition. Yeah, but in general, we do ribbon calculus in tensor category because ribbons have twist. Well, if I go like this, for string, we can just make it straight. There's nothing happens, but for ribbon, there will be a kink, and that's a topological twist. So we're interested in the anyon tunneling map, and how is that related to the ribbon operator? So we now want to look at some variant because I've been mentioning the word subphase, what it is. In Hector's paper, they define this kind of a variant of quantum double by introducing a subgroup M of G and a normal subgroup N included in M. So this corresponds to 2 operators where T is just restriction to the subspace where only M happens, and Ln is a quotient. We're identifying every element in the normal group N. So let me give you some example. For S3, we can take M to be where sigma is the flip part in the permutation group, and tau is the rotation cyclic part in the permutation group. And we can take M to be E and sigma, and N to be E, the trivial group. Then the qubit is just the E and sigma, and nothing interesting happens here. If we take M to be the original S3 group, and N to be the quotient, the cyclic part, and then the physical effective physical qubit will be reduced to the qubit where the state 0 is E plus tau squared, and the other one is sigma times N. So that's what they do. They make like qubit-wise restriction. Then correspondingly, with these 2 operators implement, we can add some, U and put U to be larger and look only at the low energy sector. And then corresponding to that, A will be modified to AM, where we only sum over the subgroup M, and N. Previously, N is taken to be E, the trivial unit in group. And now it's N because in quotient group, N is trivial. So this model realizes quantum double M over N, the reason I've just explained. And we're only looking at these subphases, the subspace of these two operators. Okay, so this is one of the main pictures in this talk. We are looking at three different phases. We try to figure out how anyon is condensed, as you can see from P2 to P1 or P1 to P2. Here, P0 is the original quantum double, and P1 is M over N, and P2 is M prime over N prime. So we talk about
say that I had an operator as 10 to the 10 G. What is the coefficient, this one coefficient? How fine tuned it has to be to see that behavior?
Is that the question?
I don't know.
Or is this?
Could whoever asked the question over Zoom, can you like type it in the chat, please?
Okay, I'll just continue, and maybe later I'll check the chat. And we only need to specify the boundary term, because we talked about the interior part already. So the boundary term are designed as this. Again, you don't need to like remember this. It's designed in such a way that every term commute with each other. And we want to know exactly what the ribbon does to the state, because it will review how an anyon turns through different phases. So we define gamma to be this whole ribbon. And then the algebra of the ribbon operator. Recall that F operator is that it excites only the two ends because it commutes with every term in the Hamiltonian. And then to find something similar to F, we want to commute with everything in the Hamiltonian except those on the two ends. And that operator must look similar to F. And here it turns out that the answer is this. There will be summation over the two quotient groups. And here we define some subset of G cross G. And this subset S is used to make sure that it commutes with the projection terms, the Tm and Tm primes that I mentioned before.
So this ribbon has support on this on the verge on here, like this block.
Yeah, across the whole middle and enters these two. All right, so that operator defined here as a property. This identity gives us the equivalence relation because such multiply conjugate H by N prime and multiply G by N prime and multiply to the right by N. This gives a equivalence class on G cross G because H and G were originally taken across all products in G. So that means because of this equivalence relation, the number of parameters are reduced from G squared, because this is a pair, to only G squared over N times N prime, the order of groups. And then the lemma is that the operator that we defined before, the G operator, when they act on the ground state of the Hamiltonian, they form a set of orthonormal bases of two-point anyonic excitations located at the two ends. So that's kind of our whole point and what we expect. All right, and just like particles are representations of groups in high energy. Please go ahead.
Yeah, like kind of a basic question. So on one side you have the theory M over N, and on the other side you have M prime over N prime, and you have like a ribbon operator that presumably is serving as some map between the anyon theory M over N to the anyon theory M prime over N prime. Are there any like restrictions on like what M over N and M prime over N prime can be? Like for example, do they have to be of the same size so that the map is like mapped between?
That's a very, very good question. Not necessarily. And the only restriction is that M and M prime are subgroup of G, And the n and n prime are normal subgroups of G, and they are contained in M and M prime respectively. That's the only constraint. And the two like different theories don't need to have the same dimension. It can be quite different.
So the map between the anyons on one side and the anyons on the other side doesn't have to be like an isomorphism, like.
No, for example, we will consider I will later give an example on one double S3, and that is how that is turned out to the Topological. So that's quite different. Okay, so just like in high energy theory, yeah, please.
So if originally your ribbon is not a form presented before, but if it is like inside the face and then you do a projection, like the single projection, will it become the ribbon as the form we presented before?
Yeah, possibly, but I'm not sure how to make such a projection. So I have to like resort to, to get this G operator, I have to go through a lot of computation requirements, like using my hand, how to figure out I have to calculate the computation relation of the local terms. Like it's hard to find such a projector. And okay, so my point is that, it's always a slogan that particles are repetitions groups, symmetries. Here it's same. Particles are a repetition of the algebra of one level. So on the right-hand side, which is a partial one gamma on the right-hand side, it's a repetition of the quantum double M over N. If you don't know what the algebra quantum double is, it's actually here the definition. So it's indeed a repetition of it. And on the left-hand side is a repetition of M, quantum double M prime over M prime. And then we can use the good old trick to do the character theory. So to define character, we need to implement the argument or parameters will be the parameters of the algebra. So algebra here is quantum double M over N, tensor product, quantum double that one. And that's the input. Okay, so the character is defined by taking the trace for each such input. The trace is defined previously here by using this as a acting G operator on the ground state. That's our basis. So taking such a trace will arrive at kind of a complicated formula, but it's explicit for this tunneling map. So how do we use such character? We first, okay, I have to remind that the character for the ERAP quantum double is already known a long time ago. So this is for one copy of the quantum double, not like the two copies that I put before, just one copy. And we'll use orthogonality because we know that the characters in the character space, they are kind of orthogonal to each other. And we just need to decompose the character formula that I written before into this kind of a basis in the character space. And here, the other basis. So what I mean is this formula. So these two are known. That is just what I showed in the last slide. These two are known. And by using orthogonality, we take the inner product with this guy. And here on the left side is what I written before. We will use the inner product to get this coefficient. This is just a number. All right. So this number is what I call as the anyon tunneling map. This integer will tell us what anyon is mapped from one theory to another. So the anyon types for the quantum double S3 is given here, where it's given as a pair of parameters C, which are the countries classes in the group, and R is a representation of the centralizer of that representative in that countries class. Representative of countries class is what I call the RC, a centralizer of this guy, and we take its representation as R. So there will be 8 anyons in the theory, and for the story code, there will be 4 anyons. All right, let's do some exercise. So if we take M as the free part of the permutation group and N to be the trivial one, then we can use the previous formula to get all those integers. The only non-zero integers are these numbers. So if we copy this, we can read off how anyon is condensed. A is condensed 1, B is to E, C is to 1 and E, D is to M. So it means that part of C will be the E anyon in toric code, and the other part will be vacuum, and D will be the M anyon, and so on. And for the other situation where M is the whole group and it's cyclic part, then this condensation is almost the same as the previous one, just switch C and F because these two theories are due to each other. Okay, let's go back to the Floquet code. Is there any questions? I've been moving kind of fast. Okay.
So could you go back to the previous one?
Yeah, sure.
Just making sure, so, can you give some intuition what the E and maps do for me?
Like how is this is mapped?
The last one, E maps do for me.
Okay. This is because E uses it's a non-trivial, it has a non-trivial charge and non-trivial flux. Yeah, it's a sign repetition in the Z2 group, and the condensed class is the free part.
So interestingly, that the C maps to 1 plus E means that the corner dimension of C is 2, so actually it's a sort of 0 of 1 plus E. So can I understand this?
Yeah, I think so. All right. Now, yeah, we'll try to attach ourselves back to the main topic. How is this related to the Floquet code? So actually, we'll find that anyon map 5 will be quite useful in this. So we can put the framework of this theory here by taking different M and N, because I mentioned that the color code is isomorphic to point double Z2 cross Z2. So we can use this framework to explain perfectly the Floquet code by taking different M and N. M can be taken as the second copy of Z2 and first copy of Z2 and the diagonal part. Diagonal part because in Z2 cross Z2, there's a diagonal generator. And similarly, we can take N to be the second copy, the first copy, and the diagonal part. So that's how we arrive at 6 subphases. And what if we can consider the anyon? So if we calculate it for each of the steps in the previous slide in the table, it will correspond to the identity map. It's just diagonal identity. And if we try to take some illegal steps, which were analyzed by Hastings and Han in their original paper, if it's illegal, actually it corresponds to here, the anyon map will be kind of topological. And so it's not an isomorphism. So in general, such allowed steps will be, firstly, it's a permutation group, it's full rank, it's a permutation group. Secondly, such permutations respect the modular data or the anyon theory data. It has to preserve the statistics. So besides this, I also worked out Floquet code in S3 and D4, but I won't look into them here. They are well-defined streamline process because here, just think back, the characters and the groups are like well-known, and yeah, it can be implemented by a classical algorithm to tell if such a Floquet code is possible or not, given the knowledge of group representation theory. So one important point is that the framework doesn't have the standard low weight because initially people realized that the Floquet code is good because it has low weight measurement. So it's easier than the 4-qubit measurement in various experimental platforms. But here it's my discussion here is rather theoretical and generalized for arbitrary lattice size, arbitrary lattice structure. So it doesn't preserve the engineering advantage. And I want to remark here, there's some fundamental difficulty because in the original Floquet code, the qubits lie on the vertices. And if we try to generalize this picture, it's kind of hard because for quantum doubles, we need it on the edges for it to be commuting projector, because on the edge, left and right, they correspond to left multiplication and right multiplication. And that's important because these two commute with each other. And similarly, in level 1 model, there's also some fundamental difficulty because the qubits or quantum numbers correspond to the edges in the level 1 model, or the ribbon, the tensor graph in level 1 model. And well, the vertices will correspond to different fusion channels. So it's actually quite difficult to take a naive generalization. And starting from here, is there any questions before I move on to the next topic? Okay, so if you're familiar with quantum computation with gap boundary or surface code, this will be kind of familiar to you, because in those pictures, we are trying to draw a fusion tree where the leaves are the anyons condensed to the punctures in the fusion tree in the surface code. And here, I'm just trying to say that besides the gap boundaries or the punctures, we can also put some subphase here. And then what will be the ground state? The ground state will be, first, we need to fix the shape of the tree. So the shape will, more or less represent the structure of the phase and kind of look like this. You can also choose a different tree structure, but they will be related by F move in tensor category. So let's first fix the shape of the tree, and then the ground state will correspond to all anyon labels and all tunneling channel labels. So they will correspond to a set of labels like this. All right. And here, what I've shown here is A3 minus A3 plus. Minus means the anyon after the crossing the domain wall, and this is before tunneling through the domain wall. And mu are the condensation channels. So, and then what a logical operation we have in such a picture. So this is rather similar to Iris Hong and Zheng Wang's paper in 2017, where they already discussed this kind of picture, but they took this as a puncture, as a trivial phase. Here, I'm just trying to say that it can be more than something trivial. So this wrap operator will give us the modular S matrix. And below here, I'm showing a picture from the surface code. This is a famous paper by Fowler. This is towards large scale surface code. Their title is something like that. And such a wrapping corresponds to such a wrapping of anyon E in the toric code around the puncture. And this blue one will correspond to the B here. This is the generalization of this picture. And if we try to do something crazy, and we can look at some, okay, this kind of looks kind of complicated, but the point is that I'm trying to act eternal in anyon A from one subphase to another subphase in the tree diagram. Recall that this will be our ground state. In general, there might be more than just 3 subphases. I'm just trying to illustrate here. And the calculation will be similar if we try to go like many subphases. So the point is that after this operation, we go back to our original tree. This is looks like the original, but we are left with a lot of factors. So this is our logical operation. This is a generalization. Actually, I should have shown this first. It's much easier to see. So the right line will correspond to this right line. And here I show 3 subphases, but here there are only 2 punctures. And this tunneling operation is just mapping an operator to an operator acted by Z. The last one will be braiding. Braiding corresponds to like entangle different qubits, logical qubits. This was also mentioned in their paper. Okay. And this is the surface code where such breeding happens. But wrapping one subphase around the other, this is wrapping one function around the other, we get an entangled operation on two qubits, C naught. So those are what happens if we introduce more than one phase in the spatial direction. I'm going to move on to talk about how this affects the quantum computation in the time direction. So in the conventional picture for quantum computation, we start with the initialization and we do some breeding of anyons, and then we merge those anyons. That's the full quantum computing process if we're using fusion trees executed. Here, my claim is that we can do more than one phase. We can introduce some phase transitions in the time slice. And this is because some operators are easier through breeding in one phase and might be harder in another phase. So this is a generalization of Floquet code where the different phases don't have to be isomorphic. It just can be, they're just related on a higher level. And they doesn't have to be periodic either. The only requirement is that this step is unitary because we need unitary to preserve the logical information. So I'm going to be more specific on what I mean by a unitary phase transition. So let's say we are looking at the fusion tree, and we try to make this fusion tree as our qubit. This was mentioned in Microsoft paper. They use this kind of scheme. Right? It's just that they use tau as an example. They use Fibonacci anyons in their paper as an example. Here I fix A, B, C, and D, and only vary X in the fusion tree. And this will give us a set of qubits. So here, this is domain wall. You can think of it by going back to the quantum double where I had those domain wall line here. And this domain wall, this can be viewed as both a temporal or spatial picture. So we first start with this diagram, and then we slowly move the domain wall down until you can forget about this ribbon calculus until it passes the whole graph. It will return back, return to the original graph. It's just here we are left with X prime and some linear combination factors. So the theorem will be just that we want this to be unitary. I choose here a specific fusion tree, but you can imagine, use different fusion trees. We will go through similar calculations. And the point is that we want the coefficient through the phase transition, corresponding to the phase transition, to be unitary. So one can also consider phase transitions introduced in both temporal and spatial directions, but because of limited time, I will not discuss here. It's actually that quite similar. It's just that, for example, we can introduce some subphase or gapped boundaries for this to condense to, and then make the scan of the phase transition similar as here. And you can think about, first of all, we have a bunch of different subphases in the plane, and then we make a time scan of the phase transition. So that's what I mean by introducing phase transition in both time and spatial direction. Okay, actually, I ran much faster than I expected. So here's a summary. So we have explicit formula for anyon tunneling map using the character theory of the algebra for anyon excitations. This framework incorporates and generalizes the Floquet code to not only non-abelian quantum doubles, also you can, use similar scheme for a generic, maybe 11-win model. And it's just that we replace the quantum double algebra with the tube algebra, because tube algebra is the algebra that explains the anyonic excitations in 11-win model. So this also predicts possible automorphism between the subphases of the parent quantum double. That's what I mean. I mentioned this previously by using the anyon tunneling map, and I claim that if we want isomorphic basis, then we need it to be a permutation matrix, and this also has to respect the anyon theory, the modular data in the anyon theory. So at the end, we push the idea further to generic phase transitions, both spatially and temporally in TQC, as long as they amount to unitary transformations on logical QDIS. So this is a much less restriction than periodic isomorphic phase transitions. So this generalization will give us more logical gains in TQC. Okay, that's everything. Thank you so much.
A couple of questions during the talk. Does anybody have any further questions or comments?
Yeah, please.
I know that it's technical, but can you briefly summarize what's the Floquet code for DS3? Like, what's the lattice, what's your measurement schedule, what are the phases you can get?
Oh, right. In DS3, if we want conventional Floquet code, there are only two subphases that are isomorphic. That's let me try to go back to Shellgun and Arcos diagram. Okay, there are only these two.
What do you measure at each time step?
We will be measuring the T and L operators. I think I showed somewhere, but T and L, we want the resulted state to be in the plus eigenstate. They are the two projectors or POVMs, and that's what we measurement. We do the measurement. So their Floquet code is kind of trivial. The Floquet code will be going from here to here, from here to here, and so on. That is kind of trivial than the Z2 cross Z2.
Sorry, I'm not familiar with the like guide version of this Floquet code. So like in each cycle, how many time steps do you have? Like 2 time steps?
Yes, because that's the only allowed subphases here in this picture.
So each time step you measure both T and L every
Yes. Yes.
T and L defined for the S rate.
T and L specify for each subphase you want to consider, right? And for D4, it's actually quite enriched. We have a way a lot of more allowed Floquet code. Yeah, in the paper, I give the list of possible steps. It's actually much richer than the original Floquet code. No.
Maybe it's because D4 is like Z2 semi-group hooked up with D2 times D2, so actually you have some other structure from this semi-group.
Yeah, I guess so. Yeah, please.
You talked about logical gates, implementing logical gates using these protocols.
Using either fusion tree, because there are two schemes in topological quantum computation. One is fusion tree, the other is gapped boundary. I talked about. I think I touched on both schemes.
So maybe for both, what are the minimal topological orders you need to get universal gate sets?
That's a different topic. Yeah. And it's actually kind of hard, first of all, to classify topological orders by whether or not they are universal or not. That's a very hard question. And in Arison and John Hahn's paper, they discussed some of that, but it's far from a complete classification based on universality. I only know some examples, but I don't know how to answer this question in general.
Yeah, but just examples would be, can you give some examples which are universal?
Yeah, I think DZ3 is a universal set in John Hahn's paper. for example, and the Z2 definitely not, because we need magical distillation. Yeah, and add.
This is with the gap boundaries. Does it get up in the gap boundaries?
And in Sean Cui's paper, I forgot which group they used, but they used a different scheme, which is the fusion tree, a direct breeding of anyons. Yeah, I forgot if they claimed anything like that. Yeah, please.
So in like gapped boundary computation, like there's like a perspective where kind of applying the automorphism is equivalent to like inserting like a invertible domain wall, and like the kind of applying this invertible domain wall is equivalent to like pumping an SPT across the system. And if you do certain types of SPTs, you can get like a universal gate set, like a 2+1 DSPTs. They're like some similar perspective here. Like if I apply like if I look at two different subphases, like M over N adjacent to M prime over N prime, where you also have this like unitary criteria, like what is living at the boundary interface of the two phases?
Okay. Yeah, first of all, I have to admit I'm not familiar with the scheme. You first like intro to me. Yeah, maybe we can talk more about that. It sounds very interesting. Second, here. What's between that? First of all, you can, kind of put a background DG here, but you can remove it or take this white part to be infinite, like thing. It doesn't matter. So I think to answer your question, what's in between is this boundary term. It's designed such that it remains to be a commuting projector model. And yeah, that's the domain wall. Any other questions? Yeah, please.
For the anyon tunneling map, is it possible? So you show examples where you can map non-abelian anyons to abelian anyon. Like say some of the non-abelian anyon S3 to like the E and M anyons in C2 target code. So first of all, is the tunneling map like, can you always construct a reverse direction? Is it always well defined?
Okay.
If so, then like what internal state?
Yeah. So actually, when I say like A is turning to B, B can also turn back to A.
Yeah, so
it's always kind of
if
reverse.
you have like a abelian anyon in say Z2 target code, if you were to tunnel back to say S3, then which internal state of the non-abelian anyon would it be?
It will be written in the same equation will give that. So if I say A and B, A to B, then immediately we will know that B can also go back to A. That's what that equation.
Maybe let's take one of the example you have, like the E anyon maps to like the F fermion, like the F in target code. So like since like E is the non-abelian anyon, where you have like 3 internal states,
right?
So if I were to have a F anyon and then tunnel through back to S3 to form double, then which internal state of this E anyon would it be in?
For the exact like a local internal degree of freedom, this work doesn't explain that because it uses category theory. It uses calculus theory summed over the internal degree of freedom. In other words, I think what you're trying to asking, if I understand correctly, is that you want to know the exact CG coefficient of such fusion. By CG coefficient, I mean the basic quantum mechanics of fusing two things. One look internal degree of freedom. This work doesn't do that. And as far as I know, and also we don't think anybody has done that. It's kind of complicated.
But at least you think that it exists. You can always go from.
Yeah. If we have F to the right, it will only go back to E, and no possible any other possibility.
But theoretically, it should be possible to
figure out which
It
particular
dep-
internal state it
it-
goes back to. or-
Yeah, and also it depends on domain one. Here I'm fixing the domain one. If the domain one is fixed in this, by this condition.
At least the fusion, like say like fusing two anyon
And
to get
it's also possible that here, my restriction here is that it doesn't accept any cost energy, confined energy. It doesn't accept any of that. So that's also one of my requirements. So what I'm saying that if in my picture, so if after going back to the left-hand side, I'm requiring it doesn't leave any track of energy, any like confinement energy. So that's the other requirement.
Yeah, Margarita asked a question. She asked, sorry for the naive question. Perhaps I missed this. What is the precise definition of Floquet code that you are using? How do you ensure that the logical information is shared between different phases in your framework?
The first is that I keep mentioning the using the word conventional Floquet code, by which I mean it's maybe periodic or not, but it's isomorphic of subphases. And I said that it has to satisfy this definition if it's a permutation group of anyons, and second of all, it respects the modular data. That's the two requirements. And here, I think the biggest generalization will be just phase transitions of two allowed different phases. They don't have to give the same isomorphic modular data, but they have to be unitary. Okay, that would be my definition. Yeah, please.
Can I have a guess in the previous questions? Like, because E has three internal states, right? And F only have one. So I think when he makes the domain work, he actually choose the representative of this continuous class. And then when you pass that, you actually the F will become the certain states, like for example, if you choose like 1, 1, 2, and then it will be 1, 2, and maybe the non-trivial representation of the centralizer. So I think this is a guess, but I don't know.